Welcome to fifth lectures on terpenes and terpenoids. In this lecture, we are going to discuss about the chemistry of alpha terpenol molecule. We will discuss the occurrence as well as uses of terpenol. The structure determinants of alpha terpenol will be discussed on the basis of chemical methods of analysis, and at the end, we will discuss the synthesis of alpha terpenol. Now let us see from where we get the alpha terpenol. The major source of the alpha terpenol is the pine oils. This terpenol molecule is a mixtures of various structural isomers. Terpenol molecule exists as alpha isomer, beta isomer, gamma isomer, and it is also called as a 4-terpenol. Now out of these 4 isomers, the percentage of alpha terpenol is measured in pine oils. It is having a pleasant odor, and the odor is similar to the flowers of lilac, and because of this pleasant odor, it is commonly used in perfume industry, cosmetics as well as flavors. Now let us discuss the structure of alpha terpenol. The structure determinations of alpha terpenol was initiated during the year 1893 as well as 1895 by Olach. The structure determination method involves chemical methods of analysis, where first of all the elemental analysis of carbon and hydrogen is carried out, and from elemental analysis chemistry to the molecular formula of the alpha terpenol, which was found to be C10H18O. Now from this molecular formula we get a lot of information about the structure of alpha terpenol. Since it contains 10 number of carbon atoms, it means there are 2 isoprene units, and therefore it belongs to a class of monoterpenite. Again, we can apply the isoprene rule to the structure of alpha terpenol. According to the isoprene rule, there is a head to tail linkage. So 2 isoprene units perhaps in alpha terpenol may be connected through head to tail linkage. So we get a broad idea about the structures of alpha terpenol just by counting the 10 number of carbon atoms in alpha terpenol. Another information we get from the molecular formula is the degree of unsaturation. Degree of unsaturation or the double bond equivalence is related to the presence of double bond as well as the presence of cyclic system in a molecule, and it is calculated by the formula x plus 1 minus y by 2. So if you keep these values here, then the degree of unsaturation in the alpha terpenol is found to be 2. So degree of unsaturation is equal to 2. It means that alpha terpenol molecule may contain the 2 double bond, or it may contain the 2 rings, or it may be the combinations of 1 double bond plus 1 ring. So in this way, just by calculating the molecular formula of the alpha terpenol, we get lot of structural informations. Now in the incoming investigations, we have to find out this degree of, we have to find out the nature of these unsaturations. Therefore, a simple experiment is performed here. Alpha terpenol was subjected to hydrogenation experiment. When hydrogenation was carried out, the resulting molecule was isolated, resulting hydrogenation product was isolated, and it was again subjected to elemental analysis, and from elemental analysis they were reaching to the molecular formula of hydrogenation product of alpha terpenol, and it was found to be C10H20O. So if you make a simple chemical arithmetic, that is if you subtract the molecular formula of the alpha terpenol from hydrogenation product, then it is observed that alpha terpenol has consumed only one equivalent of hydrogen molecule. So consumptions of one molecule of hydrogen indicates that alpha terpenol contains one double bond. Similar kind of evidence is obtained from bromination. Alpha terpenol adds to only one molecule of bromine, therefore alpha terpenol contains only one double bond. So in this way we have reached to very important structural features of alpha terpenol, that alpha terpenol contains one double bond. It out of 2 unsaturations we have accounted 1 degree of unsaturation due to the presence of double bond. Now let us see the nature of oxygen in alpha terpenol. Now for nature of oxygen we are having 4 evidences, 4 chemical experiments. This third experiment is very important. Alpha terpenol undergo dehydration with H2SO4 readily. Dehydration is a characteristic reaction of tertiary alcohol, therefore it is suspected that alpha terpenol is a tertiary alcohol. Tertiary alcohol are reluctant for oxidations under mild oxidation, and it is also observed that alpha terpenol does not give aldehyde or ketone on mild oxidations. Therefore, these two results conclude that alpha terpenol, the nature of oxygen, may be a tertiary alcohol. And if it is a tertiary alcohol, then it will not be dissolved in dilute NaOH. So if it is dissolved in dilute NaOH, the chances of phenolic substrate, but here it is not responding to the dilute NaOH, it is not dissolved in dilute NaOH. Therefore again we we may assume that alpha terpineol is a tertiary alcohol. Now, alcohol molecule can add to the phenyl isothiocyanate, and similarly, when alpha terpineol was treated with phenyl isothiocyanate, it leads to form phenylurethane molecule. So, on the basis of these four evidences, we conclude that alpha terpineol is a tertiary alcohol. And since it's a tertiary alcohol, we can rewrite the molecular formula of hydrogenation product here C10H20O. We can write it as C10H19OH. Now C10H19OH, this molecular formula corresponds to the parent hydrocarbon C10H20. So C10H20 corresponds to CnH2n, and CnH2n corresponds to the monocyclic structure of a molecule, and therefore on the basis of just simple chemical arithmetic, we have proved that alpha terpineol is a monocyclic molecule. So we have progressed a lot as far as the structures of alpha terpineol is concerned. We have proved that it contains one double bond. We have also proved that oxygen is in the form of a tertiary alcohol, and we have also proved that it is a monocyclic. We have also proved that it's a monocyclic. Now, in the subsequent discussion or subsequent investigations, we have to find out the nature of this ring in alpha terpineol. In other words, we have to find out the skeleton structures of the alpha terpineol, and for that we are having a very strong chemical evidence. When alpha terpineol was treated with H2SO4, it leads to form parasamine molecule, and the formations of parasamine clearly indicates the presence of paramethane skeleton in alpha terpineol. So if in this paramethane skeleton, if we assign the positions of tertiary alcohol, that's the OH group, and the positions of the double bond, then we will quickly reach to the structures of the alpha terpineol. So the positions of double bond as well as the positions of tertiary OH group is assigned on the basis of an interesting oxidation experiment called as graded oxidations, and it was done by Woloch in the year 1893-1895. So they treated alpha terpineol with range of oxidizing agents under different conditions, and at every stage they isolated the product, and from characterizations of the isolated product they reached to the structures of the alpha terpineol. Now let us see what this experiment is. Alpha terpineol is treated with 1% alkaline KMnO4, and we have said that alpha terpineol contains one double bond. So this double bond will be dihydroxylated. Alpha terpineol already contains one OH group. So hydroxylation introduces two OH groups, and therefore the resulting compound is a trihydroxy compound. That is a C10H20O3. So double bond is hydroxylated as well as there is one OH group. So we get a trihydroxy compound. This trihydroxy compound on oxidations with CrO3 gives one intermediate, and this intermediate rearranges to form a compound number 4. Then this compound number 4 is treated again with 1% alkaline KMnO4, and here degradation product is formed. Here 10 number of carbon atom is converted into 8 number of carbon atom and acetic acid. And again here further oxidations of terpineolic acid, that's a product number 5. It forms terpic acid with one lesser number of carbon atoms. Now this was an experiment, and if you understand the structures of terpic acid, terpineolic acid as well as this number structure 4, then we can reach to the structure of alpha terpineol. Now this product number 4 is a very important stage of the experiment. This was isolated in pure form and it was subjected to some chemical reactions, and the analysis of this 4 has shown that it is a keto compound. There are 3 oxygens here. Out of 3 oxygen, 1 oxygen was in the form of a ketone, and the nature of 2 oxygen was assigned by some different chemical evidences. When 4 was treated with sodium carbonate, it is not responding. There are 2 oxygen remaining here. One we have assigned as a ketone, and 2 oxygens we have not still assigned here. So chances is that it may be the carboxylic acid, but when it was treated with the sodium carbonate, it is not responding to this. It means that this ketolactone, this number 4 molecule, is a neutral molecule. When this ketolactone is treated with NaOH, then it consumes one molecule of NaOH to forms the carboxylic acid. So chances is that this molecule is a cyclic ester, and we can call it as a lactone. So formations of 4 we can assign as a ketolactone. Ketolactone on oxidations with KMnO4 from acetic acid, and the formations of acetic acid is possible only when we assume this ketolactone as a methyl ketone. So methyl ketone, and here is a lactone. Lactone must be formed by the cyclizations of the carboxylic acid with the OH. There are three hydroxy groups. Ketohydroxy acid is formed here. So this one hydroxy group is remaining intact because tertiary alcohol does not get oxidized. So on the basis of this experiment, chemists reached to the structures of ketolactone. Similarly, they have assigned the structures of terpineolic acid as well as terpic acid on the basis of its synthesis. And the structures of terpic acid was found to be this lactone. The structures of terpineolic acid was found to be again keto acid lactone. And here is a formations of acetic acid, and formations of acetic acid clearly indicates that this is a methyl lactone. It's a methyl lactone, and this methyl lactone must be formed due to the cyclization reaction. It's a tertiary OH groups, and therefore this ketohydroxy acid might have been formed as an intermediate. This ketohydroxy acid is formed by the cleavage of this double bond, and therefore we can assume this dihydroxy compound is a trihydroxy compound. It's a tertiary alcohol remains intact, and at the end we can reach to the structures of the alpha terpineol in this way. So we have this oxidative degradation experiment is a turning point of investigation as well as the structure of alpha terpineol is concerned, and we have now reached to the structures of the alpha terpineol. Now once we have assigned the structures of alpha terpineol, it's time now to convince ourselves with the help of again the same reactions. This particular experiment requires more discussions and a better understanding of the topic. So alpha terpineol on 1% alkaline KMN4 we have seen it forms trihydroxy compound. One OH group is already here, so we get a dihydroxylations of this double bond and we get a trihydroxy compound. On CrO3 oxidation, this remains intact, but this diol gets undergo cleavage and we get a ketocarboxylic acid, and as soon as this acid is formed, it is trapped by this hydroxyl group to form the lactone. This is a methyl ketone, and this methyl ketone on reactions with KMnO4 undergo degradations here, and we get terpineolic acid, and terpineolic acid is subsequently further oxidized to form the terpic acid. So in this way we have reached to the structures of the alpha terpineol on the basis of graded oxidation experiment, and this is a very important experiment as far as the entire structure investigation is concerned, and it was the very old era of Volage when it was 1893. So almost very old investigation was carried out on the basis of very simple chemical. They reached to the structures of alpha terpineol. Now the structure of alpha terpineol has got support from the synthesis of these two intermediates, terpic acid and terpineolic acid. They were independently prepared in the lab and their properties were compared with the graded oxidation experiment. This is easy to prepare from ethyl acetoacetate. Both of the compounds can be prepared from ethyl acetoacetate. It is base catalyzed alkylation reactions, and then its reactions with the methyl magnesium bromide here. In both the cases we required the help of Grignard as well as the base catalyzed alkylation reactions. So we get here hydroxy acid, and this hydroxy acid undergoes cyclizations to form the terpic acid. Similarly here, instead of one equivalent of ethyl chloroacetate, it is treated with the two equivalents of ethyl chloroacetate. We get a dialkylation here, and then decarboxylation occurs here, and again here it is treated with these two ester groups are protected with the help of ethanol. It's esterified, and then it is treated with only one equivalent of methyl magnesium bromide. We get a tertiary alcohol, and during the hydrolysis these two ester groups are hydrolyzed to the carboxylic acid, and it cyclizes to form the terpineolic acid. So this is a very interesting synthesis of terpic acid as a terpineolic acid. Yet every lactone is formed by the cyclizations of the hydroxy acid, and before this hydroxy acid is obtained by the Grignard reactions. So this this ketone, methyl ketone, is subsequently treated with the Grignard reagents in the sequence of reactions. Now once the structure determination of alpha terpineol is achieved, now it's time to talk about the synthesis of alpha terpineol. It was carried out during the year 1904 to 1908, and this synthesis is very interesting. We have to prepare this alpha terpineol molecule. So the base starting material is the paratolvic acid. So paratoluic acid is converted into alpha terpineol with the help of again simple reagents. Here it is sulfonated followed by KOH fusion. Sulfonation is required here because we want double bond on this side, and for that in the beginning we carry out the sulfonation and followed by KOH fusion. We got here phenolic carboxylic acid, and this phenol undergo reductions with sodium in ethanol. We get this compound, we get cyclohexanol type of the substrate, cyclohexanol, appropriately substrate cyclohexanol. Then its reactions with HBr gives bromination and elimination reactions occur, and we get a double bond. Later on, this carboxylic group is esterified and it is treated with the two molecules of methyl magnesium bromide, and we get the alpha terpineol. So this is a very interesting class of synthesis, how it is planned. The starting material selection is very meticulous. As a paratoluic acid is prepared as a starting material for the synthesis of alpha terpineol, and we have made only efforts to introduce this OH here, sorry, the double bond here, and we have also made the efforts here to make the tertiary alcohol, and for that the Grignard is the best strategy. So in this way, we have learned the synthesis of alpha terpineol, and now with the development of Diels-Alder reactions or pericyclic reactions, uh, a very simple synthesis of alpha terpineol was accomplished by combinations of two reactions. One is a Diels-Alder reactions followed by Grignard reactions. So isoprene and the methyl vinyl ketone undergo cycloaddition reactions called as a Diels-Alder reactions, and then its reactions with the methyl magnesium bromide gives alpha terpineol. One can also make limonene from the same intermediate by using the Wittig reactions. So in this way, Adler proposed the short synthesis of alpha terpineol using the Diels-Alder reactions as a key step. So in this way, we have completed the synthesis of alpha terpineol. Now it's time to talk about the applications of alpha terpineol in the synthesis of other terpenoid molecules. Alpha terpineol on Alpha terpineol can undergo dehydration, we have already seen, and there are various ways to dehydrate it. If it is dehydrated with the oxalic acid, this terpinolene is a monocyclic terpene and it's an optically inactive, whereas alpha terpineol is optically active. So we get the synthesis of terpineol by dehydrations of alpha terpineol. Similarly, this alpha terpineol can be dehydrated with potassium hydrogen sulfate. Here, limonene is found to be the major product, and plus some quantity of terpineol is also obtained. Similarly, synthesis of carbon can be accomplished from alpha terpineol, and for that, very interesting pathways involved. Alpha terpineol undergo Markovnikov's additions of nitrosyl chloride. Here nitrosyl NO plus, the positive portion is NO plus and negative portion is Cl minus in this reagent, and the addition occurs according to Markovnikov's rule. Then this nitroso is in tautomerism with the oxime, so we get the isomerization here, and oximes, then this oxime chloro compound undergo eliminations. In presence of sodium ethoxide, we get a more substrate double bond here as a major product, as a Setzer product. And in hydrolysis, both the things are happening. Oximes is hydrolyzed to the carbonyl group, as well as this alcohol is undergoing dehydration to the carbon. So this is a very beautiful reaction sequence leading to the synthesis of carbon molecule. So we have learned now alpha terpineol chemistry right from beginning. We will see how we started it. We have determined the molecular formula, then we have performed hydrogenation, bromination experiment, and then we made some parasamine formation was there, and from that we reached to various structural features of the alpha terpineol molecule, and the positions of one double bond as well as the tertiary OH group is established on the basis of graded oxidation experiment. And in graded oxidation experiment, the analysis of each substrate was carried out, and the structure of this molecule number 4 is very important. It was proved to be the ketolactone, and from that we reached to the structures of the alpha terpineol very well. And as soon as we reach to the structure of alpha terpineol, we have convinced ourselves how this graded oxidation was occurring. Trihydroxy compound is obtained by cis hydroxylations of this alkene, and then in oxidations this OH group remains intact. It's a tertiary OH group. It undergoes spontaneous cyclizations. We get a methyl ketone, and later on this undergo degradations and we get a terpinolic acid as well as terbic acid, and structures of terbic acid and terpinolic acid was proved on the basis of this synthesis. Similar synthesis is accomplished from paratolvic acid. Here, uh, this tertiary group is introduced to the Grignard reaction, and for the introductions of double bond, we have performed sulfonations as well as KOH fusion reactions and the elimination reactions. And applications of Diels-Alder reaction is demonstrated for the synthesis of alpha terpineol also. And at the end, we have seen how alpha terpineol is useful in the synthesis of two important monocyclic monoterpinide like terpinolene, limonene, and the carbon. So in this way, we have learned the chemistry of menthol. Now, once we have learned the chemistry of menthol, now we have to check our progress, how much we have progressed, and for that we have to solve some problems. Now, there are variety of the problems. Some of the problems are here listed. So students should undertake these problems. Here some statements are given. For example, the molecular formula is C10H18O. It adds to the one molecule of bromine or hydrogen. So whatever the chemical evidences, chemical facts are there, chemical evidences they are shown, and from these chemical evidences, the student is supposed to derive the conclusion about the structure of alpha terpineol. So this is one variety of problem. Second is about the Diels-Alder reaction. It's a very attractive synthesis of alpha terpineol. Alpha, it can be employed for the synthesis of limonene and alpha terpineol. And the next one is synthesis of terpinolic acid using ethyl acetoacetate chemistry. There are two equivalents. So molecular formula of the intermediate products is also given here. So on the basis of that, the student is supposed to write this reaction sequence. And at the end, the synthesis of alpha terpineol from paratolic acid can be asked in two different ways. Here is a this here is a synthesis of menthol. By mistake, this has happened, and here the synthesis of alpha terpineol is shown here, where these two are somewhat parallel because it's a menthol is here, and here is a alpha terpineol. Both of them are starting from aromatic compounds, and how aromatic compound is functionalized to get this alpha terpineol. It is shown with the help of these two problems. So in this way, we have learned the chemistry of alpha terpineol. In the next lecture, we'll discuss about the chemistry of camphor molecule, and subsequently we'll cover all these structural elucidations of remaining dozens of terpenite molecules. Thank you. Thank you very much for watching the video.